Download this code from codegive.com, link in the description below. OK, let's dive into a detailed tutorial on event-driven applications, drawing heavily from Julian Wood's excellent GoTo 2022 presentation. We'll cover the core concepts, benefits, challenges, and walk through a practical code example to solidify your understanding. Title: Building Event-Driven Applications, a deep dive, inspired by Julian Wood's GoTo 2022 talk. Introduction. Event-driven architectures, EDA, have become increasingly popular for building scalable, resilient, and adaptable applications. Rather than relying on synchronous, tightly coupled communication between services, EDA decouples components by exchanging asynchronous events. This allows for greater flexibility, independent deployments, and improved responsiveness to changes. Julian Wood's GoTo 2022 talk provided a compelling overview of the benefits and patterns for building modern EDAs. This tutorial aims to expand on those concepts, providing a more hands-on approach with code examples. What are event-driven applications? In an event-driven application, components, services, functions, modules, react to events emitted by other components or external systems. An event is a significant change in state, a signal of something that has occurred. These events are typically asynchronous, the producer of the event doesn't wait for a response from the consumer. Decoupled, the producer and consumer don't need to know each other's internal details. Immutable, the event itself represents a past occurrence and cannot be changed. Key components of an EDA. 1. Event producers. These are the systems or services that generate events. They detect a change in state and publish an event to an event bus or message broker. The producer is only responsible for generating the event, not how it's processed. 2. Event bus/message broker. This is the central nervous system of the EDA. It's responsible for receiving events from producers and routing them to the appropriate consumers. Common technologies include Apache Kafka, a distributed streaming platform known for high throughput and fault tolerance. RabbitMQ, a versatile message broker supporting various messaging protocols, AMQP, MQTT. AWS EventBridge, a serverless event bus service on AWS that integrates with many AWS services and SaaS applications. Azure Event Grid, the Azure equivalent of EventBridge. Google Cloud Pub/Sub, a scalable, reliable, global messaging service. 3. Event consumers. These are the systems or services that subscribe to events and react to them. They listen for specific types of events and perform some action when they receive one. Consumers are independent and can scale independently. Benefits of event-driven architectures. Decoupling. Services are loosely coupled, reducing dependencies and making it easier to modify or replace individual components without impacting the entire system. Scalability. Event-driven systems can scale horizontally by adding more consumers to handle increased event volume. Producers are also free to generate events without worrying about overwhelming consumers. Resilience. If one consumer fails, it doesn't necessarily impact other consumers or the overall system. Events can be persisted in the event bus, allowing consumers to replay events after recovery. Flexibility. New consumers can be added to the system to react to existing events without requiring changes to the producers. Real-time responsiveness. Events can be processed in near real time, enabling faster responses to changes and improved user experiences. Auditability. Events can be persisted for auditing and historical analysis, providing a clear record of system activity. Asterisk integration. Asterisk edas can easily integrate with other systems and services, both internal and external. Challenges of event-driven architectures. Asterisk complexity. Asterisk managing distributed systems with asynchronous communication can be more complex than traditional monolithic applications. Asterisk debugging. Asterisk tracing events through the system can be challenging, requiring robust monitoring and logging. Asterisk eventual consistency. Asterisk data consistency can be eventual, meaning that it may take some time for changes to propagate through the system. Asterisk ordering. Asterisk ensuring the correct order of events can be difficult, especially in distributed systems. Asterisk idempotency. Asterisk consumers must be designed to handle duplicate events, as events may be delivered more than once. Patterns for building event-driven applications, inspired by Julian Wood. Julian Wood's Goto 2022 talk emphasized several key patterns. Here are some important ones. 1. Event sourcing. Asterisk instead of storing the current state of an entity, store a sequence of events that led to that state. This allows you to reconstruct the current state at any point in time and provides a rich audit trail. You can also replay events to create new projections, different views of the data. Asterisk example, think of a bank account. Instead of just storing the current balance, you store every deposit, withdrawal, and interest payment as an event. You can then calculate the current balance by replaying all the events. 2. CQRS, command query responsibility segregation. Separate the read, query, and write, command, operations of your data. This allows you to optimize each side independently. Typically, you'd use event sourcing for the write side and create materialized views for the read side, making reads fast and efficient. Asterisk example, in an e-commerce application, writing data, placing an order, updating inventory, goes to one system, and reading data, displaying product listings, showing order history, goes to another. 3. Saga pattern. Asterisk a saga is a sequence of local transactions that together fulfill a business transaction. It's used to manage distributed transactions across multiple services in an eventual consistency manner. If one step in the saga fails, compensating transactions are executed to undo the previous steps. Asterisk choreography-based saga. Asterisk each service listens for events and decides if and when to execute its local transaction and publish new events. Asterisk orchestration-based saga. Asterisk a central orchestrator service coordinates the saga, telling each service when to execute its local transaction. 4. Dead letter queues, DLQs. When a consumer fails to process an event after multiple retries, the event is moved to a DLQ. This allows you to investigate and resolve the issue without blocking the processing of other events. 5. Event enrichment. Asterisk consumers can enrich the events with additional information before processing. This can be useful for adding context or performing calculations. Code example, a simple order processing system. Let's illustrate these concepts with a simplified example. We'll create a basic order processing system using Python and RabbitMQ. This example focuses on the messaging aspect of EDAs, leaving aside event sourcing, CQRS, and Saga for brevity, but we'll mention how they could fit. Assumptions asterisk. Asterisk you have Python installed. Asterisk you have RabbitMQ installed and running, or a Docker container with RabbitMQ. See RabbitMQ's official documentation, https://www.rabbitmq.com/download.html, for installation instructions. Asterisk you have the Pika Python library installed, pip install Pika. 1. Order producer, order_producer.py. 2. Inventory service, inventory_service.py, event consumer. 3. Payment service, payment_service.py, event consumer. 4. Shipping service, shipping_service.py, event consumer. 5. Dead letter exchange, DLX, and dead letter queue, DLQ, set up in RabbitMQ. You need to set up a dead letter exchange and dead letter queue in RabbitMQ. This is usually done through the RabbitMQ management UI, typically accessible at http://localhost 15672 if you're running RabbitMQ locally, or using the RabbitMQ command line tool. Here's how to do it using the RabbitMQ management UI. 1. Create a DLX*, go to the Exchanges tab and create a new exchange. *name, dead_letter_exchange. *type, topic, or direct if you prefer. *durable, true, recommended. 2. Create a DLQ*, go to the Queues tab and create a new queue. *name, dead_letter_queue. *durable, true, recommended. 3. Bind the DLQ to the DLX*, go back to the Exchanges tab, select the dead_letter_exchange, and add a binding to the dead_letter_queue. *routing key, this means all messages routed to dead_letter_exchange will be sent to dead_letter_queue. 4. Configure the main queues, the queues used by the consumers, to use the DLX*. When you declare the queues for the inventory service, payment service, and shipping service, you need to add arguments specifying the DLX. You cannot do this through the UI after the queue has been created. You need to either delete and recreate the queues, or, preferably, modify the Python code to declare the queues with the dead_letter_exchange argument. For example, in inventory_service.py, change the queue declaration to. Do the same in payment_service.py and shipping_service.py. This tells RabbitMQ that if a message is rejected from these queues, using basic_nac with requeue equals false, it should be routed to the dead_letter_exchange. Running the example. 1. Start the consumers*, open 3 terminal windows and run the following commands in each. 2. Start the producer*, in a 4th terminal window, run. You should see output in each terminal window indicating that the order is being processed. If everything works correctly, the order will be created, inventory will be checked, payment will be processed, and shipping will be initiated. Demonstrating failure and the DLQ. To demonstrate the DLQ, let's simulate a failure in the inventory service. Change the check_inventory function in inventory_service.py to always return false. Now, run the producer again, Python order_producer.py. You should see in the inventory_service.py output that it detects insufficient inventory and calls publish_inventory_reservation_failed. The payment_service.py should then pick up the inventory.reservation.failed event, and call the cancel_order function. Because the inventory service called chbasic_nac, delivery_tag equals method.delivery_tag, requeue equals false, the failed order message will be routed to the dead_letter_exchange and then to the dead_letter_queue. You can then inspect the dead_letter_queue in the RabbitMQ management UI to see the failed order message. This allows you to analyze the cause of the failure and potentially retry the order manually, after fixing the underlying issue. Enhancements and further exploration. This is a very basic example. Here are some ways to enhance it and explore more advanced concepts. Error handling and retries. Implement retry mechanisms with exponential backoff for transient errors. Use dead letter queues for persistent failures. Idempotency ensure that consumers can handle duplicate events. You can use a unique identifier, example order ID, and store it in a database to track processed events. Saga pattern implement a saga to manage the entire order process, including compensating transactions for failures. Consider using either a choreography-based or orchestration-based approach. Event sourcing replace the simple check _inventory and update _inventory functions with an event sourcing implementation. Store inventory changes as events. CQRS create separate read and write models. The write side uses event sourcing, and the read side uses materialized views. Monitoring and logging implement robust monitoring and logging to track the flow of events through the system and identify potential issues. Use correlation IDs to trace events across services. Testing write unit tests and integration tests to ensure the correctness and reliability of your event-driven application. Consider using tools like ptest or unitest. Schema evolution carefully manage schema changes to avoid breaking compatibility between producers and consumers. Use schema registries like Confluence Schema Registry to enforce schema validation and evolution. Message format use a standardized message format like Avro, Protobuf, or JSON schema to define the structure of your events. Julian Wood's key takeaways: reinforcement. As Julian Wood emphasized in his GoTo 2022 talk, remember these core principles. Events are facts. Treat events as immutable records of past occurrences. Design for eventual consistency. Accept that data may not be immediately consistent across all services. Embrace decoupling. Keep services loosely coupled to improve flexibility and maintainability. Monitor everything. Implement comprehensive monitoring and logging to track the flow of events and identify potential problems. Choose the right tool for the job. Select the appropriate message broker and other technologies based on your specific requirements. Conclusion: event-driven architectures offer significant advantages for building modern, scalable, and resilient applications. By understanding the core concepts, patterns, and challenges, you can leverage EDA to create more flexible and adaptable systems. Julian Wood's GoTo 2022 presentation provides a valuable framework for thinking about EDA, and this tutorial has aimed to provide a hands-on approach to applying those concepts. Keep exploring, experimenting, and building. Good luck.